Firstly, welcome everybody. It's really great to have you all here. So this is just a little mini workshop that KITP was very kind to agree to host to us, just to take stock of the developments that have happened since the very productive workshop back in the spring of 2017. And our first speaker in a moment is going to be Yvonne Geyer, who's going to tell us about quadratic propagators from the worldsheet.
Well, thank you so much for the invitation, and thank you to all the organizers for putting this together. I guess I have the pleasure of being the first speaker due to time differences. And it's a real pleasure to be back, and at least virtually, for this reunion after that, as David said, after having a very productive meeting back at KITP. And I'm actually very glad to talk about something that, at least via various detours, arose out of some of the conversations that we had during those weeks back in KITP. I should say this is some work together with Ricardo, both Montero and Ricardo Stark-Michel, and Arthur Lipstein and Joe Ferro. And what I want to talk to you about today is a problem that we've sort of known about for a very long time, which is that the most promising worldsheet formulations for quantum field theories that we have right now suffer from a big issue, which is that at loop level, at least, it seems as though they give rise to a very unconventional integrand formulation or representation. And just to situate this a bit more for you, what I want to focus on today is a specific representation of quantum field theory amplitudes as coming from a worldsheet theory. We've known at least since Witten's twistor string that this exists, and it has seen a considerable uptake more recently, first through the CHY formulae and then through the Ambi twistor strings that underlie these formulas. Now, like all worldsheet formulas, the real power of these models is that they give you the full amplitude or integrand at higher loop level, just as coming from a single Riemann surface. Now, in some sense, these models still remember, or in a very real sense, they remember that they're describing a quantum field theory. And one way that you can still trace that in these higher loop contributions is that you can reduce them, the full answer, to a much more simple expression that lives on a nodal sphere. Now, I want to focus today on what happens at one loop, though, to be honest, in the spirit of this conference, I should have really talked about two loops, since that was what really came out of the discussions at KITP, but I just grew a bit intimidated of putting all the technicalities of that into a 30-minute talk. So you're hearing about one loop today. So I will briefly talk about what the one loop answers look like that we've known for some time by now and that were developed by David, Tim, and Eduardo, and the reduction to the nodal Riemann sphere. And then what we'll see is that the integrand representation that you find there is what you could call a linear representation. And I will tell you what that is and how it relates back to the standard Feynman or quadratic propagator representation that we know. And so obviously there's a question of whether we can get back Feynman propagators either directly once you have the integrand, or even better from the worldsheet. And at least for supersymmetric Yang-Mills theory, I will tell you today how that can be done. Okay, so the brief overview of what we're going to do is we're going to start at tree level and then slowly work our way up to the nodal Riemann sphere at one loop. Okay, so just as a brief review, the CHY amplitudes are among the most compact known expressions for the S-matrix for massless field theories that we know to date. And what they do is they express the amplitude in terms of an integral over the moduli space, m naught n, of marked Riemann spheres, where I've denoted the marked points here by sigma I. Let me stress that this is for massless quantum field theory, so I will always take Ki to be the massless momenta, null momenta, and living in d dimensions at this point. I don't want to make any restrictions on the dimensionality. The special property of these formulas, however, is that they're completely local. The integrals are completely localized onto some constraints that are known as the scattering equations, and I've denoted them here by EI. Now, how you construct them is actually quite simple. You just construct a one form on the sphere just by summing over all particles. This is an n-point amplitude with ki over sigma minus sigma I. And then the scattering equations just tell you that the residues of p square vanish at all marked points. Or more geometrically, it tells you that p square vanishes everywhere on the sphere. Now, a simple counting tells you that I've put a prime here to indicate that you have to mod out by some symmetry that is essentially just the Möbius invariance. So there are n-3 of these constraints in here, which measures exactly the dimension of the moduli space, so the full integral is completely localized. So really, this is just some of the solutions here. Now, last but not least, we have the integrand here. And while the rest here, notice that I haven't made any statements about what massless quantum field theory I'm talking about, and that is because all the scattering equations and the measure is completely universal for all massless quantum field theories. The integrand is what carries really all the information about what type of quantum field theory we're talking about. So this integrand I here carries all the data, say the color structure, the polarization of the particles. And for all relevant theories that we know, it splits nicely, or at least for everything that we're going to talk about, into two what are called half integrands that I've noted here by IN 1/2. And just to give you a bit of a feeling for how these look like, don't worry about the details too much, but what I want you to take away from this slide is just that they're relatively compact and that the color structure is something that should look very familiar. It's just a Park-Taylor factor. Whereas if you want, the kinematic part is a reduced Pfaffian, which is just a Pfaffian that you've reduced by some symmetry, where the symmetry is given on the scattering equations, on the constraints. And the beautiful part is that you can really see the double copy structure in this integrand, where the gravity integrand consists of two Pfaffians, one Pfaffian, and here I've introduced the tilde for the corresponding polarization, whereas Young-Mills has one copy of the color, one copy of the kinematics, and you can also construct a biojoint scalar theory with two copies of the color structure. Now, a lot more theories have been written down, but today we're mostly going to focus on gravity and Young-Mills theory. Now, the construction might look a bit ad hoc, or it might not feel it immediately intuitive for why this should give you a correct quantum field theory amplitude. And just to motivate it a little bit, let me point out a very important correspondence to you, which is that the scattering equations, well, let me first say, in the integrands, all poles, as you can see, sit in the sigmas. So all integrands are completely polynomial in the external data. That means all poles of the amplitude lie at the boundary of the moduli space. And what the scattering equations do for you is they map this boundary of the moduli space to factorization channels of the amplitude. And so this is a very concrete correspondence that you can check in great detail, but the crucial driving factor here is actually something that you can do on the back of an envelope. It's just a really short calculation, which is the following. Describe the boundary of the moduli space just by some punctures coming together. So here I've denoted the punctures coming together to a joint point sigma L, and epsilon is some small parameter that governs my degeneration here. So that parameterizes the moduli space around this boundary. Then you can just construct this combination of the scattering equations, and you can see that on the support of the scattering equations at the boundary of the moduli space, the propagator that you're expecting becomes on shell to leading order in epsilon. So the scattering equations give you a correspondence between the boundary of the moduli space and all the poles that appear in the integrands and factorization channels of the amplitude. And that is what is really driving these amplitude formulas. Now, at this point, you should be asking yourself, or if you know the answer, maybe not, where the Riemann sphere really came from in here. And hopefully, or you would hope that the answer to this is that there's some underlying worldsheet model. And one of the reasons you might hope for this is that once you have a model, you can use it for various different purposes. So you might try putting it on a curved background, or in our case today, you might try to use the model to calculate higher loop contributions. Now, the CHY formula were very much discovered directly by ingenuity, but it's much harder to do the same for higher loop contributions. So the model is really the driving force here that tells you that you can do this. Now, there is indeed such an underlying model, and it is what is known as the Ambi twistor string. It has been developed by Lionel Mason and David Skinner. Now, I won't have the time to give you a lot of details. I just want to give you sort of a brief feeling for what the model looks like. And you can see that it has a p dot d bar x minus a constraint e tilde p square here. And I've put in the type 2 the supersymmetric model, and hence why I've called it RNS. Now, the important part here is that everything is chiral. So both my fermions are left moving. And you can see that we have chiral reparameterization invariance here. Now, this in principle looks very similar to world line formulations. And once you do a full BRST quantization, the beauty of this model is that you actually end up with 3 linear CFTs. And that means correlators and everything is relatively easy to calculate. Now, the critical dimension, basically the same counting as in a string. Most of these calculations work very, very similarly to the RNS string, is again 10. So for the model, for the type 2 supergravity model, we will be working in 10 dimensions here. Now, it's easy to see that the target space is Ambi twistor space, which is where the name is coming from, and which is just the phase space of complexified non-geodesics. So you can see that we have P and X, and we're modding out by the P square constraint. Now, the spectrum after GSO projection is just type 2 supergravity, and I've given here an example of one of the vertex operators. And I really want to stress here there are no stringy modes. It's type 2 supergravity on the nose. And without going into any details, what you can do is take tree-level correlators of this model, and what you find is that they directly reproduce the CHY amplitudes. Now, without giving you any details of the calculation, there's one important point that will recur also at higher loops that I do want to highlight, which is that the vertex operators, the fixed as well as the integrated, only depend on x through the exponential. And that means that you can integrate out the px system and find that p fully localizes onto its equation of motion, which is d bar p is ki delta bar sigma minus sigma I. And when you solve this, we find the solution for p that we saw before in our construction for the scattering equations. And then you can, at least heuristically, hopefully see that the scattering equations will come out from carefully quantizing the constraint p squared that we imposed in the action. Now, with this, we can actually use this and move on to loop level. And the good news is that David and Tim and Eduardo did the hard work for us. And once you calculate the correlators, what you find is the following. The amplitude can always be written as the integral over, we'll come back to this d10L in a second, but the moduli space M1n of the torus with n marked points, which just consists of n minus 1 points. The translation invariance of the torus allows you to fix 1 marked point, and the modular parameter tau that is invariant under tau going to tau, everything is invariant under tau going to tau plus 1 and tau over tau plus 1. So really we're integrating that modular parameter over the fundamental domain. Now, the L here comes out of the same localization constraint that we saw before for P. So really what we do is now we solve this localization constraint, the equations of classical equations of motion, but on the torus. And the L's are nothing but the zero modes, and I've suggestively called them L because they will have a connection to the loop momentum. Here dz is just the holomorphic differential, and omega is the one loop meromorphic differential with plus minus one residues at mark points I and some reference point that I've called here 0. Now, as before, the scattering equations tell us just that p square has to be 0 everywhere, in this case on the torus. And in fact, that means we know how to construct most of them, even if I didn't go through the derivation with you, because we know that we can just set the residue of p square at the marked points to 0. Now, in contrast to tree level, this doesn't guarantee that p square is 0 yet, because p square at this point could still be proportional to dz square, what I've called the proportionality factor u here. So clearly we're missing one more equation that I've put in here with delta bar u that just tells us that this coefficient is actually vanishing as well. Now, I'm sweeping under the rug all the details of the integrand because that is a bit more involved, but we'll come back to that in a second after we've simplified this. Now, there's two properties of this that I want to highlight for you. One is that the integrand I is again fully localized. So it's a very similar counting to before. You're integrating over n-1 mark points plus the modular parameter, and you have n-1 plus 1, so n scattering equations that fully localize it for you. The other important point is that the whole expression is actually modular invariant. Note that this doesn't tell you that it's finite, because we are integrating with the D10L over a non-compact modular space. But these two properties will play a very important role in just a minute, because as beautiful as this construction is, it is really hard to see how it connects with any representation of quantum field theory amplitudes or integrands that we know. So it's, while it's a beautiful mathematical construction, it's not very intuitive or easy for us to work with. And in particular, solving these constraints is really hard. So ideally, we would like to have a way of relating this back to at least something that is more directly related to the way we usually think about quantum field theory integrands. And the way to do this is to use the two key features that I was highlighting to you before, the localization and the modular invariance. Together, they tell you that you can actually apply a residue theorem on the fundamental domain. And the argument is really simple, but just let me spell it out for you. Think of having solved all the other scattering equations, what I called EI before, the residues. Then you're left with one scattering equation, which I called U, just for the modular parameter tau. Now I've drawn it here schematically as the solutions as some points on the fundamental domain. Now the residue theorem tells you that you can equally well wrap the contour around and pick up all the other poles that are sitting in the integrand. Now it turns out that the integrand has no other poles apart from the pole at tau equals I infinity, by modular invariance, effectively. And so the only pole sits at tau equals I infinity, or equivalently at Q, which I've defined here, equal to 0. But geometrically, this is exactly the degeneration of the torus, where you pinched one of the cycles, as you've seen here. And this directly corresponds to a Riemann sphere with a node, so with two additional marked points that you glue together. Now, when we do this in the amplitude, the formulas massively simplify. And let me stress this is the full integrand here that we're talking about. We're not making a cut or anything, but the residue theorem tells you that the two expressions are exactly equal. Now, after all the simplifications, what you find is obviously, so we've just discussed that we're integrating over the moduli space of this nodal sphere here. And what you find is that P becomes just L times 1 over sigma minus sigma plus minus 1 over sigma minus sigma minus, plus the term that we saw before already at tree level. So this looks very much like a forward limit. And importantly, it has the same complexity as tree level. So this whole formula will now be much easier to work with. Similarly, the scattering equations now take the form p square minus L square omega plus minus square, and geometrically it tells you that p square is not 0 anymore, but p square minus L square omega plus minus square. Now these are still Möbius invariant and everything, so the same degree of freedom counting that we did before still tells you that the integrand is fully localized as it should be. Now, there's 3 comments that I want to make here. The first one is to notice that these scattering equations are actually linear in L. Now this is easy to see, just look at the form of P, and we're subtracting out the quadratic term in L, so everything is linear. The other 2 comments is that because the complexity is now similar to tree level with 2 additional points, this is something that we can very much work with. And last but not least, so all of these were originally we worked in 10D for supergravity. And sometimes we're getting a free lunch here because now all of these formulas are actually valid not just in 10 dimensions, but in arbitrary dimensions D. From the perspective of the worldsheet, this tells you that there are no non-trivial winding modes. And also we can use double copy principles to find different theories. Let me be brief here, but just to say that from supergravity we can extrapolate to super Yang-Mills, where we introduce an additional building block, which is a Park-Taylor factor with a cyclic structure here, where we sum over where we've inserted the node. And similarly, you can construct non-supersymmetric theories. The only thing I want to highlight is that these the formulas for the kinematic part simplify drastically if you just consider MHV, basically due to the fact that BCJ numerators are known at one loop for MHV. Okay, so we've already alluded to this, but let me highlight the strange feature, if you want, of this, or the peculiar feature of this integrand representation. So we have the overall 1 over L square, which came from the U scattering equation that sits out front from the residue theorem. And all the rest, all the other poles that we said can only come from the scattering equations. But the scattering equations are linear in L. So we have something that seems to carry the wrong dependence in L. Now, the solution to this is actually quite simple. There's a simple partial fraction identity that you can apply to a standard Feynman type integrand and some shift in the loop momentum. And this has been formalized into a whole procedure known as Q-cuts, or we're going to use here only the first part of these Q-cuts. But instead of telling you the whole procedure, let me just give you an example because it's hopefully a bit more intuitive, which is the following. Let's just look at the massive bubble here. This is the simplest non-trivial example, just with a 1 over L square L plus K square. Now, using this partial fraction identity, we get 2 terms, and we can already see that both of these terms are now linear in the loop momentum and have 1 quadratic term. And then clearly we can use a shift in the loop momentum to bring the second term into the form that there's an overall 1 over L square. And so the claim is that the integrand representation that we get out of this will be of the form that we see here on the last line. There's obviously a different way to see this, or a more systematic way, and it's basically just an extrapolation of what we've seen already at tree level, just using the correspondence between the boundary of the moduli space and the factorization chance. Now, we've seen what the problem is. So these are linear propagators, which means if we want to do anything with these formulas, like integrate or anything, all the methodology that's been built up around integrating the integrands will be of no use to us. So basically there's 2 options. One is rebuild all the work that has been done for standard Feynman propagators, for linear propagators, which sounds like a huge amount of work and I'm very much not qualified to do. Or we have to think about whether these linear propagators are actually an intrinsic feature, or whether we could have also arrived at a formula with standard quadratic propagators on this Riemann sphere. And so we're taking the second route because, as I said, the first one I'm very much not qualified to do. And to sharpen this a little bit, let me just point out, so I told you how to go from the Feynman representation to the linear representation. So we know if we have quadratic propagators how to get the linear ones out. So we can very much compare answers that we get just by expanding a known integrand into the linear representation. What we don't know how to do is, if I hand you a linear representation, determine, even if it is something that recombines to a standard Feynman representation of anything, and even less how to go back. Now, the reason we don't know this is that it's actually at the level of the integrands, it's quite hard. And you can see that even in a reasonably easy example. The easy example is just look at an n-gon. So I've spelled it out here, and I've done a partial fraction identity and some shifts to get it into the 1 over L squared times something form. Now, if you know, which we usually don't, that this has an origin in terms of a quadratic propagators, you could think of a very naive algorithm that you could try. Something like picking out the first term and then just substituting all the linear propagators that you see in a convenient way by quadratic ones. And one way to do it is putting 2L.K1 to L plus K1 square and 2L.Kn to minus L minus Kn square. This clearly does the job. Now we can already see that this is very limited. So the easy way to see that is looking for a different cyclic ordering, for example. And what you can see here is that this will already not give, for a different cyclic ordering, this will already not give you the correct quadratic propagators. So the naive algorithm that I told you about already fails for the first non-trivial example. Even worse, already for an n-1 gon, it fails for any reasonable interpretation of how you would do this shift at the level of the integrand, this moving through L.K1 to L plus K1 square. Because if you take a BCFW-like shift, you can see that you will screw up the massive corner term. It's actually really easy to see why, but I think I'm running a bit low on time. So let me cut that a bit short and just tell you. Sorry?
About 3 minutes remaining.
Okay, so let me just tell you that the reason it goes wrong is that you basically just picked up one term in the BCFW loop recursion, whereas you should have picked up 2 terms. Now, what actually works and what I want to tell you about in my last few minutes is to do the modification not at the level of the integrand, but at the level of the worldsheet. So what I want to do is take this naive algorithm, which is why I even told you about it, and turn it into an algorithm at the level of the worldsheet formulas that we know. So now it's very easy to see, instead of picking out the first term, what we want to do is in the color half integrand, remember I told you this has a cyclic structure, we only want to keep one term there. And the substitution that caused us so much problem if we try to do it with a BCFW-like shift, it will actually be fine if we do it directly at the level of the scattering equations. Now, let me just briefly tell you what this looks like very quickly, and then tell you why it works, and then tell you what I would actually like to tell you. So what it looks like is very simple. So we saw the scattering equations for the linear formalism. You can see I've spelled them out. They have all of these linear terms. So if we want to deform the scattering equations by putting L plus K1 square and minus L minus Kn square for 2L.K1 and 2L.Kn, this just introduces some quadratic terms here. And Nebius invariance works the same as before, basically because all the L square dependence cancels pairwise. Now, if you want to see why this deformation, you can do it again systematically using the correspondence between the boundary of the moduli space and factorization channels. And what you can see is that where originally you found these linear type propagators, with the deformation, you actually pick up always the correct quadratic propagators, given that the ordering is cyclic, which is why it was so important that we also restricted the color half integrand to have the correct cyclic ordering. Now, with this, let me just briefly summarize what the whole formula looks like to you. So we have, as before, the overall 1 over L square and a similar measure, but now with these deformed scattering equations. And the building blocks are now this non-cyclic Park-Taylor factor. And for the kinematics, it is very clear that it works for the MHD case. So I've spelled this out here. And we've checked that this works both for the seed amplitudes for 4 and 5 particle integrands and that it factorizes correctly. And it's very natural to propose that this could extend more generally beyond the MHD case by just using the same kinematic integrand that we had before for the super Young-Mills case. Let me highlight that this has only a chance for working for supersymmetry. If you want, I can give you some details on that, but it's rather technical, so let me just leave it as a statement here. Now, the proposal is at this point unproven, mostly due to technical difficulties. So it's very hard to check that this factorizes correctly just because of the form involved and sort of doing the calculations with 2 fermions in the loop. Okay, so hopefully I've told you that at least in some very specific cases for super Young-Mills theory, it is possible to get to a nodal Riemann sphere formula, worldsheet formula, with Feynman propagators, with quadratic propagators. Now that said, let me tell you what I would have liked to tell you, but couldn't because it's very much work in progress. And it's, I think, the story that should be told, but that hasn't been told yet, which is the following. I think what would be really nice to see is how this comes out systematically from a residue theorem. Now, the way this would go is the following. Remember, the original argument goes like this. You have the u equals 0, which I've drawn here, and then you take the residue theorem and you land on the nodal sphere. What I've failed to tell you there is that you have some freedom here on the torus that you lose after the residue theorem, which is the following, which is not manifest after the residue theorem, which is the following. You have the freedom to add on u to any of the other scattering equations. So do that, add on u systematically to the other scattering equations, and then repeat the residue theorem. What you will find is something very much like the expressions that I gave you, but in this case for supergravity. And the formulas will be more complicated. And yeah, I think that is very much the direction that we're taking this right now. And I would very much, this is very much what I would have liked to tell you, but maybe next time if there's another reunion meeting like this. Thank you very much.
Thank you. So we have time for questions. If anybody would like to ask a question, please just raise your hand within participants. Atul, you have a question?
So can you also think of this as adding something to directly the differential P of Z instead of the scattering equations? Like something holomorphic that dies when you compute a D bar?
Sorry, you're hoping that, sorry, let me find the slide.
I meant that you added U to the scattering equations, right? So
yeah.
I was wondering if you can directly add it to the worldsheet solution for P of sigma. Something more basic. That squares, when you take P squared, it gives you the correct.
That would just give those terms. I don't know. It doesn't look immediately possible to me, but it might be worth looking at. Yeah, I can't see immediately that it would work, but there might be some additional freedom there that might be worth looking at.
So I'm just wondering if that's a gauge choice of how you worked with the model in that sense.
It is very much a gauge choice. Sorry, let me go back to the residue theorem slide. So the gauge choice is effectively in the model, what type of Beltrami differentials you use.
Right.
So you're using Beltrami, when you're integrating out when you're BRST quantize and you integrate out, the way you get out the scattering equations is that effectively you chose a basis of Beltrami differentials to sit out front. And if you had chosen something different, you could have very much ended up with these deformed scattering equations that I was talking about.
That's what I was also wondering. Yeah.
So that is very much true. That in that sense, I mean, that's why at the level of the formulas, it's completely equivalent, and that's just reflected in the fact that it's just a basis choice for the Beltrami differentials that you use.
Cool, thanks.
Okay, so Lance, you have a question?
Hi, Yvonne, nice talk. So I was curious, suppose I don't want to get the integrand in a quadratic form, but I want to jump directly to the integrated result. At one loop, could I use generalized unitarity, quadruple cuts, triple cuts, etc., on the linear form? I think it would work fine, if at least if I knew the color order, the ordering of the particles, which I might in Yang-Mills.
Yeah, for Yang-Mills.
Is supergravity more difficult than Yang-Mills in this respect?
I think at one loop you might still be fine.
Okay.
There's been some sort of small comments that sort of basically you have to be a bit more careful with unitarity, because you generalized unitarity, because the propagate, I mean, in some sense it's built for quadratic propagators. So you're using in some sense the fact that you know that it has an underlying format that has quadratic propagators. But as you said, sort of at one loop, I think at least it works fine.
Yeah, I mean, if you assume that there is a representation like that, then I think that the procedure of taking the residues of the functions probably doesn't care whether it's linear.
Yeah, that might also be, at least at one loop, that might also be
right.
something good to look at. And you're also alluding to something that might be interesting, which is that in principle, there might also be very much smarter ways to directly arrive at some Schwinger parametrization for doing these integrals. But I don't know if anyone has actually looked at that in great detail.
Thanks.
I have time for a couple more questions.
I guess I can ask a question, David, if that's fine.
Please do.
I don't see a button for the raising hand. So I had a question. You mentioned that the construction requires SUSY, otherwise something goes bad. Maybe can you elaborate on that a little bit? Also say how much SUSY, because I missed that part.
Oh, I didn't say it. My suspicion is that any amount of supersymmetry will work, and that just non-supersymmetric theories will not work, but I have at this point no proof for this. So the problem is the following. Already in the linear formalism, it is known that there are some specific solutions to the scattering equations that always exist that are slightly problematic, and these are known as degenerate solutions. And that is basically just what happens when the node pinches. So if you look at the node here, when the two marked points actually collide. And it is important that, as in, if you want, you can think of this as something like a tadpole contribution. It's not quite, it doesn't blow up, but it will give you very much terms that you don't want and that don't look as though they do anything nice. Now, in the linear case, it's been shown that for non-supersymmetric theories, these contributions integrate to zero. And that very much relies on the fact that everything is linear in the loop momentum. Now, we've made this problem worse in two ways in this formalism. So first of all, by cutting out the cyclic sum in the Park-Taylor factors, which was crucial for getting the correct propagator structure at all. Just the power counting in when the tadpoles appear is already earlier. They get cancelled by supersymmetry. And secondly, it doesn't look to me, or it's not clear to me that the same integrating to zero argument will work again. That would have to be checked carefully, and at least sort of a quick glance at it doesn't seem as though it goes through. But maybe something smart could be done there. So that means that you really need some kinematic integrand here that cancels the naive tadpole-like contributions that you get with some power so that they don't contribute. So it definitely works for maximal supersymmetry, which we've checked, but I highly suspect that some lesser degree of supersymmetry might also work.
Thank you.
Just from sort of similar power countings in the linear case.
I don't see any further raised hands, so maybe I could abuse my position and ask a question myself. So Yvonne, to what extent, I didn't quite understand to what extent your procedure is now completely algorithmic, and to what extent you still have to be a little bit inventive as to where to put these extra factors of k.
Sorry, the procedure is completely algorithmic in the sense that it works for MHV, super young mills, and it also works, it's not a very pretty formalism, but there is a sort of double copy formalism for supergravity for MHV, and there's a concrete proposal that is hard to check, but that exists for general super young mills, and maybe even let me not make a statement about general supergravity. So in some sense, it's completely prescriptive. There's a formula that we know is true, at least in the MHV case, and that might be hard to check, but that there's a clear proposal beyond MHV. What I think is really missing, at least from my perspective, is a derivation of this from the one loop integrands that you wrote down on the torus. So what I would like to see is a residue theorem that goes directly from the supergravity one to the supergravity formulas that we know, at least for the MHV cases, that they exist. Mm. And that is, I mean, that's where my speculations at the end came in. But the rest is, for MHV, at least completely checked.
Thank you very much. Let's thank Yvonne again.